In an American arc furnace building in 1908, the electrode came down in sections. The upper carbon column separated along an internal fracture nobody on the floor had detected. What fell was not a splinter. It was a compressed carbon cylinder, 2 feet across and several hundred pounds, dropping from the electrode holder directly into the molten steel charge below. The contact sent liquid steel across the furnace bay in a pressure event that lasted less than a second. But that was not the danger the men were trained to watch for. If you're new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country and what those things cost. Subscribe and leave a comment below with the next story you want us to dig into. This is the story of the electric arc furnace, the machine that brought 6,000-degree lightning into the American steel mill and the men who learned to run it before anyone had written down how. But here is what the production records of the early arc furnace era do not capture. The electrical engineers who designed the first commercial arc furnaces in the United States had precise specifications for transformer output, electrode dimensions, and furnace geometry. What they did not have was a body of operating experience. The men who ran those furnaces were learning the behavior of a high-current electrical arc in a steel-making environment in real time, on a machine that had no precedent in American industry, in a building that had not been designed to contain what happened when the arc went wrong. To understand why the RC furnace arrived in American steel mills around 1906, you have to understand what the steel industry needed that it could not get from the furnaces it already had. The Bessemer converter and the open hearth furnace had transformed American steel production since the 1870s. By 1900, Carnegie Steel's Homestead Works, the U.S. steel mills along the Monongahela River, and the great Pennsylvania steel plants that had made Pittsburgh the center of American industrial production were collectively producing millions of tons of structural steel per year. Rails, beams, plate, and structural shapes for the building, boom reshaping American cities moved through those furnaces in volumes no prior technology could match. But volume was not the only variable that mattered. Certain steels, including tool steels for machine cutting tools, high-speed steels for industrial drilling, and bearing steels for the precision machinery reshaping American manufacturing after 1900, required alloying elements and metallurgical precision that the open hearth process could not reliably deliver. The open hearth furnace ran at temperatures it could not exceed without destroying the furnace lining. The Bessemer converter was fast, but chemically uncontrollable past a certain point. For the specialty steels that American machine tool manufacturers in Pittsburgh and Cleveland and Hartford needed, the only existing process was the crucible method. It was a small batch technique inherited from cutlery making in Sheffield, England. That method produced steel in clay pots over coke fires, and it could not be meaningfully scaled. The electric arc furnace solved this problem by replacing combustion with electricity. A French metallurgist named Paul Héroux had demonstrated the arc steelmaking process in Europe in the 1890s, and by 1906 his process had been licensed to a small number of American specialty steel plants that were already producing tool steel by the crucible method and needed to scale that production past what clay pots over coke fires could ever deliver. The first commercial arc furnaces in the United States went into production at specialty steel plants across the industrial corridor, stretching from Pittsburgh's Monongahela Valley to central New York, at facilities that had been producing tool steel by the old crucible method and now needed to scale that production. These American steel plants served machine tool manufacturers and the growing automotive and industrial machinery trades, and they were the first American steelworkers to run a commercial arc furnace at full production. These were not the giant Pittsburgh structural steel mills. They were smaller operations that needed a steel-making process capable of handling chemistry, not just volume. What they got was a machine nobody in American industry had operated at commercial scale before, running on electrical technology that was itself barely out of experimental development. And the men hired to run it arrived at the furnace floor with steel mill experience that was the wrong kind for the dangers it produced. The three-phase electrical system that powered the arc furnace created hazards no single-phase industrial system produced. 3 separate electrode circuits operated simultaneously, each carrying its full current load, each capable of fault. The phase-to-phase voltage in a 3-phase arc furnace circuit was higher than the phase to ground voltage, which meant a man who knew how to stay clear of a single-phase system did not automatically know the safe clearance distances for a 3-phase arc furnace running at these currents. And the interaction between the 3 arcs through the common steel charge meant that a fault in one circuit could propagate immediately into the other 2. Could any prior steelmaking experience prepare a furnace operator for what an electrical arc at 40,000 amperes actually looked like, sounded like, and did to the building around it? The open hearth men had spent careers managing combustion heat. The crucible men had managed small batch chemistry. Neither had stood next to a sustained electrical discharge, generating 6,000 degrees in an enclosed steel shell. Leave a comment below with what you think that first shift on an operating arc furnace floor actually demanded of the men who stayed. The arc itself is worth understanding in physical terms before anything else. An electrical arc between a carbon electrode and a steel charge is not a spark and it is not a flame. It is the same category of phenomenon as arc welding, familiar to industrial workers across American manufacturing by 1910, but operating at currents and scales that arc welding never approached. It is a sustained plasma discharge, a column of ionized gas conducting electricity between 2 points, and at the current levels at which the early commercial arc furnaces operated, it was a phenomenon that had no domestic or industrial equivalent the men on the floor had ever encountered. The arc at 40,000 amperes generated not only extreme heat, but ultraviolet radiation at intensities sufficient to cause permanent retinal damage in seconds of unfiltered exposure. The visible light from a working arc furnace was bright enough in the early furnace buildings to be seen through the building walls from the street at night. The electromagnetic field generated by the current in the bus bars and power cables connecting the transformer to the furnace was strong enough that unsecured ferrous material on the furnace floor would physically move toward the energized conductors when the arc was struck. The operating temperature of the arc exceeded 6,000 degrees Fahrenheit. For comparison, the surface of the sun is approximately 10,000 degrees Fahrenheit. The arc in the steel mill furnace was operating at more than half that figure inside a building in upstate New York or western Pennsylvania, sustained deliberately, controlled by a mechanical regulation system and the judgment of a man standing at the electrode control station. The electrodes that carried the current into the furnace were cylinders of compressed carbon, manufactured to specific grades depending on the current they were required to carry. The largest early commercial furnace electrodes were up to 24 inches in diameter and weighed several hundred pounds per section. Each electrode column was held in a mechanical clamp connected to a regulation system that raised and lowered the electrode to maintain the correct arc gap between the electrode tip and the steel charge below. That gap was measured in fractions of an inch. Too close, and the arc would short against the steel, flooding the circuit with uncontrolled current and potentially destroying the transformer. Too far, and the arc would extinguish, requiring a restrike that sent a voltage surge through the entire electrical system. The regulation system had to hold that gap through an entire heat lasting several hours, compensating continuously for the electrode tip burning away as the arc consumed the carbon, and for the steel charge level rising as solid scrap melted into the liquid bath below. What does it mean to maintain mechanical precision within fractions of an inch continuously on a component the machine is simultaneously destroying? An electrode column shortens as it burns. In an environment where the arc tip exceeds 6,000 degrees and the molten steel below it is turbulent and in constant motion. The early mechanical regulation systems solving this problem were built from components designed for simpler industrial applications, and the men servicing them between heats were maintaining equipment that had been running at the outer limit of its design specifications since the day it was installed. But the electrode regulation system, for all its mechanical complexity, was not where catastrophic failure originated without warning. The power transformer was where catastrophic failure originated without warning. Early electric arc furnace steelmaking transformers were custom-built units, each one a different design from the last. There was no standardized arc furnace power transformer in American manufacturing in 1906. Each installation required a transformer designed from first principles by an electrical engineer working with reference to European installations that operated on different power systems and at different scales. The transformer stepped utility voltage down to arc operating voltage while stepping current up to the working range, and it did this continuously through heats running for hours at a time. The thermal loading on the transformer windings operated at the upper limit of what the insulation systems of that period could sustain. Internal transformer failures produced flashovers that sent high voltage current into the furnace shell, the electrode holder, the bus bars, and anything connected to them. Transformer rooms in early arc furnace buildings were documented as extremely hot working environments with limited ventilation because the electrical engineers designing those first American installations had not yet determined through actual operating experience how much heat a continuously loaded arc furnace transformer generated in a confined industrial space over a full production campaign. Could any industrial electrician in 1908 have been fully prepared for the failure modes of a transformer that had never existed in American manufacturing before his plant installed one? The men who maintained those arc furnace transformers were industrial electricians applying general electrical experience to a machine that was more demanding than anything general electrical experience had prepared them for. An industrial electrician in 1908 had almost certainly worked on mill drive motors, overhead crane electrical systems, and industrial lighting. He had not worked on a transformer carrying tens of thousands of amperes that ran without interruption for hours and generated its own heat in a room nobody had adequately ventilated. The knowledge required to maintain those transformers safely was not available in any manual, and the electricians who developed it did so the same way the electrode operators developed their knowledge of the arc by working on the machine until the machine taught them. The electrode operators who ran the early arc furnaces were a specific category of steelworker that did not exist before the arc furnace. They were not electricians, and they were not open hearth furnace operators. They were something the machine itself created, men who had started on the furnace floor in the first years of American arc steelmaking, and who built their understanding of arc behavior from direct observation of a phenomenon that no American technical manual described in operational terms. A three-phase arc furnace required an electrode operator managing 3 electrode systems simultaneously. Each electrode carried its own arc, its own regulation circuit, and its own current load. The 3 arcs interacted through the steel charge below in ways the regulation systems could compensate for, but never fully eliminate. A disturbance in one arc, a gap excursion or a local turbulence in the molten steel surface, could propagate through the charge and destabilize the other 2 within seconds. The electrode operator watched all 3 arc systems at once, reading the current meters and the arc behavior simultaneously, making adjustments that kept the heat running smoothly through an entire melt cycle. The arc furnace floor workers at American specialty steel plants worked 12-hour shifts. The Pittsburgh Survey's 1907 wage documentation recorded skilled furnace workers in Allegheny County plants earning between $1.65 and $2.50 per day. The arc furnace operations drew their workforce from the same pool of immigrant steel workers who staffed the open hearth shops, Bessemer converter buildings, and rolling mills at Carnegie Steel, U.S. Steel, and the independent Pittsburgh area steel plants, primarily men from Poland, Hungary, Slovakia, and the Italian regions who had arrived after 1890. The Pittsburgh survey estimated that 30% of workers in Allegheny County steel operations in 1907 were recent immigrants working in classifications that required no English and rewarded physical endurance over any other qualification. The arc furnace required more than physical endurance from its floor crew, but the industry's hiring practices had not yet established a separate classification for it. The Pittsburgh survey documented that Allegheny County steel workers in 1907 worked an average of 72 hours per week, including the long turn, a 24-hour shift worked every 2 weeks when day and night turns exchanged without a rest day between them. The long turn was universal in steel mill operations of this period. An electrode operator at the end of a long turn had been awake for 24 hours and was managing 3 simultaneous arc systems, each capable of destroying the power transformer if a gap excursion was not caught and corrected within seconds. But the arc furnace asked something different from those men than any prior steel mill floor had asked. The open hearth operators had physical danger that was visible. Radiant heat from the furnace front was intense and continuous, and a man who stood in the wrong position relative to a tapping ladle was in a situation he could see and move away from. The arc furnace produced electrical danger that was invisible until it materialized. A phase-to-ground fault in the electrode holder system produced no warning sound and no visible change in the arc before the fault current found its path. The magnetic field around the energized bus bars was not detectable by any sense available to the man working beside them. The ultraviolet radiation from the arc produced no immediate pain whatsoever. Arc I, the retinal burn caused by unfiltered ultraviolet exposure from the electrical arc, typically produced its full symptoms hours after exposure. The inflammation and light sensitivity that signaled the damage were delayed, which meant a man who had been watching the arc without adequate eye protection went home at the end of his shift with no indication of what was happening to his retinas and woke at 3 a.m. with his eyes swollen shut and unable to tolerate any light. How do you build a set of safe working practices around a hazard you cannot see, cannot feel, and will not know you encountered until you wake, unable to open your eyes? How do you protect men from an invisible injury when the machine was installed before the injury pattern was documented? Leave a comment below. If you are finding this history as important as anything we have covered on this channel, go ahead and hit subscribe right now and leave a comment below with the next story you want to see. The eye protection question on early arc furnace floors was not resolved by a single decision or a single piece of equipment. Dark glass lenses adequate to filter arc ultraviolet radiation existed by 1910, but consistent use required a level of safety discipline that the early installations had not established. The furnace foreman needed to see the charged surface through the furnace door to evaluate the state of the melt, and looking through a dense filter lens gave less visual information than looking without one. Men who had spent years around open hearth gas flames had calibrated their instincts about radiant exposure, and those calibrations did not transfer correctly to the electrical arc. The open hearth flame was bright and intensely hot, but did not produce the specific ultraviolet wavelengths the electrical arc generated at tens of thousands of amperes. A man who knew how to protect his eyes from a gas flame was not automatically a man who protected his eyes from the arc. The distinction was not obvious, and in the first years of American arc furnace operation, it was not being systematically taught. The electrode breakage problem was different in character, but comparable in its fatal consequences for the men standing closest. Carbon electrodes manufactured in the first years of American arc furnace production had grain structure inconsistencies that could not be detected before installation. A column under current load and thermal stress could fracture along an internal grain boundary that showed no surface defect. The fracture propagated under the combined mechanical and thermal load of the arc cycle, and when it completed, the lower section of the electrode dropped into the steel charge below. A 24-inch electrode column was a substantial piece of material. Its fall into the liquid steel produced a steam event from residual moisture flashing in contact with the 3,000-degree melt, and the steel surface responded in a way that was not contained by the furnace walls. The men working closest to the furnace, at the moment of an electrode failure, the operator at the charge door, the electrode control man, and the tap hole crew preparing for the pour, were within the radius of that event. In Allegheny County, Pennsylvania, the industrial center of American steel production containing Carnegie Steel's Homestead Works, the U.S. Steel Edgar Thomson plant, and dozens of independent steel mills and fabricating operations, the Pittsburgh Survey's industrial fatality records between 1906 and 1910 documented electrical burns and arc-related injuries appearing in steel mill accident reports for the first time. The survey's authors noted specifically the novelty of the injury category. Prior to arc furnace installations, electrical fatalities in American steel mills were rare and typically involved maintenance workers on mill drive systems. The arc furnace added a new injury profile to the American steel mill floor, one that did not require physical contact with a conductor and could occur at distances the steelworkers themselves had not recognized as hazardous. But the electrical engineers who designed those early arc furnace installations understood the hazard in theoretical terms. They had calculated current levels, specified insulation requirements, and designed regulation systems to minimize arc instability. But there was a measurable gap between what the engineering drawings described and what the men on the furnace floor encountered, and that gap was not visible in the installation specifications. The production records of the early American arc furnace plants show engineers adjusting electrode grade specifications and regulation system parameters after each documented failure event. The knowledge base was being built from the events themselves. Each adjustment corresponded to something that had already happened. The economic case for the arc furnace was not complicated. The specialty steels it produced, tool steels and high-speed steels and bearing steels, sold at prices between 3 and 8 times the price of structural steel. A facility operating an arc furnace at capacity on those grades was producing revenue that a comparably sized open hearth shop could not approach. The facilities acquiring arc furnaces in 1906 and 1907 were under pressure to run them continuously from the moment they were commissioned, before the operating procedures were established, before the electrode grades were optimized, and before the workforce had accumulated the years of experience the machine required. The knowledge the men needed to run it safely was being built at exactly the same time the machine was being driven at full production. But what those records do not show is the full rate of arc eye injuries at American arc furnace facilities in the first decade of operation. Arc eye was not a reportable accident in most jurisdictions in the United States until the mid-19-teens. It did not appear in facility accident logs. It did not appear in the Pittsburgh survey's fatality counts because, in most cases, it was not fatal. A working man suffered permanent vision damage, and he had not been told that such injury was part of the job he had taken. That information already appears in the European literature on arc furnace operations by 1910. French and German facilities operating Héroult furnaces since the 1890s had documented arc eye in their workforces, and they established eye protection protocols as a result. Whether those protocols reached American installations in 1906 when the process was licensed is a question the production records of the period do not resolve cleanly. What those records do establish is that arc eye was present in American arc furnace workforces in the first decade of operation, and that the gap between the hazard and consistent protection lasted years. The arc furnace introduced at American specialty steel plants between 1906 and 1910 was operating at more than 500 American steel facilities by 1940, including the major U.S. Steel and Bethlehem steel plants that had started on open hearth technology and converted over the following decades. It eventually displaced the open hearth furnace as the dominant steelmaking technology in the United States. More than 70% of American steel is now produced in electric arc furnaces. The electrode operators, the transformer electricians, and the furnace floor workers who ran the first American commercial arc furnaces in Syracuse and McKeesport were the founding generation of a job category that became one of the most common in American manufacturing history. The scale of the technology they pioneered is visible in any steel-producing region of the country today, in the arc furnace buildings that are still operating on the same basic principles those first crews learned by running machines that had never been run before. The carbon electrode is still the same basic technology. A compressed carbon cylinder suspended above a steel charge, carrying tens of thousands of amperes, maintaining a gap measured in fractions of an inch. The regulation is now computerized. The eye protection is specified and enforced. The transformer design is standardized across the industry. All of that came from the knowledge built on those early arc furnace floors, one documented failure at a time, by men who were the first to encounter each failure mode. The steel workers who ran the first arc furnaces in America are buried in cemeteries outside Syracuse and McKeesport and Pittsburgh. The furnaces they learned on, rebuilt and modernized across a century of production, are still making steel. The arc they were the first to run is still burning. The steel workers who ran the first arc furnaces built the knowledge that made the technology safe. The arc they learned to read is still burning in steel mills across this country. If these are the stories that matter to you, subscribe to Steel and Sweat and leave a comment below. Thanks for watching.